Last chapter, chapter 15, Graphical Methods. So far, we know how to draw graphs of linear functions of the general form y is equal to mx plus c and use such graphs to solve simultaneous linear equations. We also know how to draw quadratic graphs of the general function y is equal to ax squared plus bx plus c and use them to solve quadratic equations as well as simultaneous linear equations. In this chapter, we will learn the last type of graphs called the cubic graphs. A cubic function is of the general form y is equal to ax cubed plus bx squared plus cx plus d, where a, b, c, and d are constants. The graphs are plotted and drawn in the exact same way as quadratic graphs. Cubic graphs, however, have two turning points. We can use the cubic graphs to solve for both simultaneous linear and quadratic as well as cubic functions. For example, draw the graph of y is equal to x cubed plus 2x squared minus 5x minus 8 for the range of x from minus 4 to positive 3 and use the graph to solve these two equations. As usual, we get a table of values for x and y. We've been given x from minus 4 to positive 3. We substitute in the equation and calculate the corresponding values of y. So we get minus 20, minus 2, positive 2, minus 2, minus 8, minus 10, minus 2, and then 22. We plot those points, and when we join them, this is the graph. Solving equation 1, we rearrange it to 0 is equal to x cubed plus 2x squared minus 5x minus 8. And then we compare it to the equation of the graph. Y is equal to x cubed plus 2x squared minus 5x minus 8. We need to eliminate the cubic function x cubed as well as the quadratic function 2x squared. We can only do that if we subtract the 2. Y minus 0 is y. If we subtract the right hand side, it will subtract out, and so we shall end up with y is equal to 0. So we find the values of x at all points where the graph cuts the x-axis, because the x-axis is the line of y is equal to 0. That will be negative 2.8, 1.3, and 2.1. So those are the solutions for the first equation. Next, we rearrange and compare the equations. Y is equal to x cubed plus 2x squared minus 5x minus 8, and 0 is equal to negative x cubed minus 2x squared minus 3x plus 3. We need to eliminate the cubic function and the quadratic function. We can do that by adding the two, because if we subtract, we will not eliminate them. So we add y plus 0 is equal to y, and then x cubed plus minus x cubed is 0. 2x squared plus minus 2x squared is 0. Minus 5x plus 3x is minus 2x, and then minus 8 plus 3 will give us minus 5. So then we have the equation y is equal to minus 2x minus 5. This is a linear function, and we can draw that line. We get a table of values. We choose two values of x and calculate the corresponding values of y. We'll choose minus 2.5 and 0. When x is minus 2.5, y will be 0. And when x is 0, y will be minus 5. We draw the line, and then we check all the points where the two graphs intersect. That is at x is equal to minus 2.7, x is equal to minus 0.8, and at x is equal to 1.5. Next, rate of change. Now on a graph, the rate of change is the rate at which the y-coordinate changes with respect to the x-coordinate. For a straight line or a linear graph, this rate of change is the gradient. And because the graph is linear, the gradient is constant throughout, and thus the rate of change is constant. A straight line has the general function y is equal to mx plus c. M is the gradient and thus the rate of change. Consider a graph of y is equal to 2x plus 5. The gradient is 2. It means that y increases by 2 for every 1 unit increase in x, and you can see that from the graph. Calculating the gradient of a straight line is easy. Change in y over change in x. But now consider a curve like this one. This curve does not have a uniform gradient. The gradient is rather changing throughout, so we cannot have a constant rate of change for such a curve. We have two types of rates of change for curves: average rate of change and instantaneous rate of change. The rate of change for this curve is speed, that is meters per second, because it's distance traveled against time. Consider points A and B. The speed of the object changes along that part of the curve, but we can get the average speed of the object between A and B by getting the gradient of the straight line AB. So we have 20 minus 5 over 4 minus 2, and that gives us 7.5 meters per second. This is the average rate of change between these 2 points, A and B. Notice the gradient we calculated is for the straight line and not for the curve. On its part, instantaneous rate of change is the rate of change at an instant, that is 1 point. Consider point A. To get the instantaneous rate of change at A, we find the gradient of the curve at A. We do that by drawing a tangent to the curve at A, and then we find the gradient of that tangent. From this tangent Mn, gradient is equal to 10 minus 0 over 3.4 minus 0.8, and that gives us 3.85 meters per second. Next, the equation of a circle. Now, consider a circle of radius r and its center at point A with coordinates AB. Again, consider a point P on the circumference of the circle with coordinates xy. Lines AB and PB meet at right angles at B. From the right angle triangle ABP, AP is equal to R, AB is equal to x minus A, and PB is equal to y minus B. Using the Pythagoras theorem, x minus A squared, that is base squared, plus y minus B squared, height squared, is equal to r squared, that is the hypotenuse squared. This is the general equation of any circle on the Cartesian plane. Examples: find the center and radii of the circles with the following equations. The first one, x minus 4 squared plus y plus 2 squared minus 4 is equal to 0. We rearrange that by taking negative 4 to the other side. So we have x minus 4 squared plus y plus 2 squared is equal to 4. The general equation of a circle is x minus a squared plus y minus b squared is equal to r squared. 4 is the same as 2 squared. So we shall have x minus 4 plus y plus 2 is equal to 2 squared. Then we relate x minus a relates to x minus 4, and if we complete that, you'll find a is equal to 4. Y minus b relates to y plus 2. If you complete that, b is negative 2. So the center of the circle is at 4, negative 2, and the radius is 2 units. Second one, x squared plus y squared is equal to 2.25. We rearrange that. This is the same as x minus 0 squared plus y minus 0 squared is equal to 2.25 is the same as 1.5 squared. So we shall have the center at 0, 0, and the radius is 1.5 units. Thirdly, x squared plus 6x plus y squared plus 6y minus 7 is equal to 0. We group the like terms together and rearrange it. X squared plus 6x in one bracket plus y squared plus 6y in another bracket. We take negative 7 to the other side and we get positive 7. We complete the square in each bracket. Remember, in completing the square, we divide b by 2 and square it. B for the first bracket is 6, and also for the second bracket is 6. So we shall have x squared plus 6x plus 6 over 2 squared, then plus y squared plus 6y plus 6 over 2 squared is equal to, we add all of them to the right hand side, 7 plus 6 over 2 squared plus 6 over 2 squared. 6 over 2 is 3, and so we shall have x plus 3 squared plus y plus 3 squared is equal to 7 plus 3 squared is 9 plus another 9. So we shall have x plus 3 squared plus y plus 3 squared is equal to 25. 25 is the same as 5 squared, and so we shall have x plus 3 squared plus y plus 3 squared is equal to 5 squared. X minus a is equal to x plus 3, and therefore a is negative 3. Y minus b is equal to y plus 3, therefore b is negative 3. And therefore the center is at negative 3, negative 3, and the radius is 5 units. Next, empirical graphs. Empirical graphs are obtained directly from experimental results, and because experiments are prone to errors, when these quantities are plotted, the points often don't lie on a straight line. For instance, these values of temperature against time, when plotted, the points are as shown on the graph. Ordinarily, we would have expected them to produce a straight line relationship, but they just didn't. And because we cannot draw a zigzag line to accommodate all the points, we estimate a line through the points which closely fits them. Such is called the line of best fit. Finally, changing nonlinear relationships to linear relationships. Now, when certain variables are plotted on a graph, they produce an approximate curve, and we've seen getting details from a curve can be quite difficult. We normally convert the nonlinear equations into linear ones and plot the relevant variables. We know that a linear graph has the relationship y is equal to mx plus c. So if we plot y against x, the graph is a straight line. Its gradient is m, and the y-intercept is c. We say that m and c are constants. Suppose I had an equation a is equal to kx squared plus h, where k and h are constants. If you relate it to y is equal to mx plus c, a relates to y, k to m, x squared to x, and h to c. So if we plot a against x squared, the gradient will be k and a-intercept will be h. Sometimes the equation may not be as direct. That is, it may not directly relate to y is equal to mx plus c. In such cases, we rearrange it to a linear one. For example, mn minus pn is equal to c, where p and c are constants. If we rearrange, mn is equal to c plus pn. Dividing both sides by n, m is equal to c over n plus p. This is the same as m is equal to c times 1 over n plus p. That relates to y is equal to mx plus c. We plot m against 1 over n. C will be the gradient, m-intercept will be p. Let us take an example. Two quantities p and q are related by the relationship p is equal to kq raised to power n. The values for p and q are shown on this table. Draw a suitable line graph for this relationship and use it to find the values of k and n, and hence the equation relating p and q. This looks much unlike y is equal to mx plus c, but we can make it that. Rewrite that p is equal to k times q raised to power n. We take logs on both sides. Remember the rules of logarithms? Multiplication means addition of logarithms. So we have log p is equal to log k plus log q raised to power n. Again, we had another law of logarithm, and if we apply it, we shall have log p is equal to log k plus n log q. Rearrange that, log p is equal to n log q plus log k. Now that looks like y is equal to mx plus c. We plot log p against log q. N will be the gradient and log k the intercept. So we get another table for logs. If we plot them, the points do not appear to be on a straight line, and so we get the line of best fit. The intercept is at 0.3, and this is equal to log k. So log k is equal to 0.3. We find the antilog, and k is equal to 2. N is the gradient, and if we take these 2 points, gradient will be 2.7 minus 1.5 over 0.8 minus 0.4, and that gives us 3. And so substituting the values of n and k, the relationship will be p is equal to 2q cubed.
One of the wonderful things about mathematics, I think, is that people are impressed. It's often seen as a very hard subject, and so if you've done math, it's often treated as an entrance requirement, as a credential to do lots of other things. And so one idea is that for example, some MBA programs, the only thing they require going into it is a good, solid math understanding. They can teach you all the business. They just can't teach you the math fast enough. And so I think that math, aside from obvious careers that require math, if you're going to go work in a department that does operations research or something like that, they'll want people with specific skills in mathematics. But math is often seen as as a filter or as a screen for many, many other disciplines. And so I guess what I'm trying to say is you can think broad, because math actually is a solid preparation. It's a good credential to go into lots of different fields that people often don't consider at the beginning.